I understand we're all a group of outsiders, so I'm perhaps the farthest lying outsider. Maybe, but I was invited, I expect, because I know something a little bit about intuitionistic mathematics, which is relevant to this group because Nicholas and Flavio are, and perhaps others soon, are interested in adapting, applying intuitionistic mathematics to physics. I accepted the invitation, even though it's somewhat inconvenient time and I can stay for only today, because I relish the opportunity to display some of the philosophical foundations of this approach to mathematics. Something, you'll see the numeral 2, that's something I'm doing in several different contexts these days. But this context is especially interesting to me because of the issue of indeterminism. Indeterminism lies at the very heart of intuitionism, but the faces of indeterminism are not often distinguished in people who talk about intuitionism, and in particular, the relation to time is often assumed, but is, as Nicholas has urged on me more than once, rarely properly spelled out. Now, one of the ways that, or the chief way that intuitionism, which is an approach to mathematics, which is called non-classical, that is, there will be an intuitionism theorems which are, will be refutations of classically accepted theorems, and some theorems which are in fact classically false. But as I said, the heart of intuitionism is taking seriously the notion of indeterminacy. Now, when I tell friends that I work on the sort of mathematics which has indeterminacy at its heart, they always raise their eyebrows. Mathematics, at least the common view, is nothing if not precise and determinate. Numbers large and small are precise. Avogadro's number, the reciprocal of Avogadro's number, is a very clear, precise thing. Arithmetic is completely determinate. If you add a pair of numbers, there is no choice as to what the outcome is going to be. When a pair of lines intersect, they intersect at a point, and that point has precise determinate coordinates. This is true of classical mathematics. Even of the more abstract, abstruse, esoteric parts of classical mathematics that these friends of mine may not know about. This is true all the way through classical mathematics, standard mathematics. But the point that intuitionists have made is that classical mathematics pays a price, in their view, a heavy price for that determinism. And that's one of intuitionism's main motivations. L.E.J. Brouwer, the founder of intuitionism, was one of the mathematics, 20th century mathematics great mathematicians, but also a great reformer. And he, together with his student Baron Heiding, and generations, now 2 or 3 generations after, objected to that price and were unwilling to pay it. And to avoid it, they fashioned what's called intuitionistic mathematics, a mathematics that refuses to pay that price, and that deviates from classical mathematics consequently in some of the ways that I've mentioned. So here's the plan for my talk. I'll tell you a little bit about that motivation, about the problems that inspired and to this day still inspire those who work in intuitionistic mathematics. Their problems mainly, the main ones are about infinity and the continuum, and I'll tell you about those problems. Then I'll quickly mention a couple of solutions that Brouwer, in fact, rejected, and then tell you the credo of the main positive program that Brouwer had for reconstructing mathematics. After doing that, I will give you what I call a taste of intuitionism. I will show you some basic intuitionistic objects and using them show you 3 deviations from classical mathematics. This is hopefully the case, but hopefully it's sufficiently indicative in order for me after that to look at the nexus of philosophical assumptions, particularly concerning indeterminism and concerning time, that underlie these deviations from classical mathematics. So when I give the deviations, I'm simply going to state them. Here's the classical principle that doesn't hold intuitionistically. Here's how we use some intuitionistic tools to validate this classical principle. I'm not going to go into the philosophical assumptions at that point, so hold your questions then. Then I will expand upon the philosophical assumptions. And that's my main brief. To tell you a little bit about intuitionism, to give you a taste, and to explore some of the underlying assumptions concerning indeterminacy and its relation to time. But in the present context, I'm going to allow myself to go one step further. I'm going to speculate. I'm going to venture some ideas about the application of intuitionism outside of mathematics in physical science. Now, this is actually a somewhat hard road to hoe, because in fact, intuitionism developed explicitly without an eye to applications. But nonetheless, I think that it's worth our while to ignore the official line of inside intuitionism, about which I will tell you, and to speculate how these ideas might in fact play out on the field of applications. There is a handout. The handout has the main definitions and quotations. Mainly, I would ask you not to look at the handout, quote for a couple of places I may read, but by and large, it's there to, if I do a definition and then refer to it later, you can look back in the handout and find it. I also have to apologize that it's full of typos. I made the handout several days ago, last week actually, before I left home and before I actually finished preparing the talk. And so I did it quickly, and I found typos this morning when I went over it for the talk. There's actually a theorem, a well-known mathematical theorem, that any handout has infinitely many typos, because for every one that I found, there's the ones that I didn't get right. One last introductory thing is I've aimed this talk at, I hope, the right level, at the level of a scientifically educated general audience. But you can never be sure. And so there will be, I expect, some things that are hard to swallow because they're outrageous. Those things I'll ask you to save in your craw until the end. But there may be things that are hard because I've gone too quickly or because they're not clear, and certainly those things stop me and ask me to explain. Okay, let's.
I'm sorry, start again. People at home are not seeing very well this slides from the camera. Is it possible? You have your email.
What do you need me to do?
Connect the Zoom.
Yeah.
Takes a minute.
Or Zoom. Or
Go to email to get the link.
You can be able to click on the link of Zoom.
this email here.
Yeah.
This,
No.
no, that wasn't the right email.
No, it's coming, it's coming. No, that was the, sorry.
That was the wrong email.
The correct email was the
Wrong link.
No, it's the wrong link.
Yeah,
It was before.
it was probably the previous email or the next email.
It's here. Yeah,
You just
there,
went by. it.
go,
This,
buzz
I
by,
feel like
go up,
we-
here, go up. There it is, there it is, yeah, that's Zoom.
Okay, well, yeah.
Then I make you co-host and you share the screen.
Right. Read whatever they want.
Your first.
Now,
You got the share screen.
Mute yourself.
You probably need to turn off your loudspeaker.
I'm mute. I'm muted.
Okay.
that's okay.
Speaker's gone now, so now we're not getting the feedback.
The green thing, yeah.
And there's this one.
And that's okay, just say okay.
Share,
You see that everyone's seen it?
and you should start also,
And
start,
this
yeah. Slideshow.
slideshow.
Make that small.
Small that.
Yeah.
There's something in
There is a
that
way to
you can chat, yeah.
Get rid of this.
Well, first check what they want to say.
Yeah. No.
Yes.
Right. And now, let's go back. Yeah. All right, this is where I am. All right, and see if that's working. Good. Okay, so, but people heard what I said up until now in the
Yeah, yeah.
introduction.
Yeah, it was just the video was not,
Okay.
it was too bright.
And so, let me start talking about the classical set theoretic foundations of mathematics. And there are some basic definitions. You know that a real number, that CM stands for classical mathematics and its ills. A real number, say the number 1/2, has a decimal expansion, 0.49999. Actually, this is a convergent infinite sequence of rational numbers, 0, 4 over 10, 49 over 100, 499 over 1,000, and continues in the same way. It's convergent because the components of the sequence get closer and closer to one another as the sequence progresses. I've given you the formal definition of convergence in the handout, but what you need to know is that as you progress, the rational numbers in the sequence get closer and closer together, and a pair of infinite sequences co-converge when their corresponding components, the nth of this and the nth of that, get closer and closer together. And for instance, the sequence that consists of 1/2, 1/2, 1/2, 1/2 ad infinitum co-converges with the sequence 0, 4/10, 49 100ths. Okay, the nth elements of these two sequences get closer and closer together. And in the classical approach, actually, a real number is the equivalence class of co-convergent sequences. And so the real number 1/2 is the set of all the infinite convergent sequences that co-converge with 1/2, 1/2, 1/2, or 0, 4/10, 49 100ths, etc. And there are infinitely many of those, and that infinite set, what the real number 1/2 is. And from these real numbers, we build the rest of mathematics. We build spaces, we build functions, we do all of the mathematics that you are probably even more familiar with than I am from these basic objects. Two problems. The first problem is the problem of infinity. I can figure out a person, a human being, can grasp in principle what an individual natural number is, even a very large number, finite collections of these, finite collections of finite collections. But how can a finite human being, this is the question that was asked, especially at the beginnings of the 20th century when these ideas became prominent. How can actually the end of the 19th, how can a finite human being grasp this three-layer cake, I call it, infinity built upon infinity, built upon infinity. The real line, the continuum is the set of all real numbers, okay? And it's an infinite set, a real number is an infinite set, and the elements of the real number, the convergent sequences are infinite objects. That is a big chunk to swallow. And how can you then build the rest of mathematics, calculus, analysis, everything else on these ungraspable things? So that's the first, in capsule, the first sort of worry that led to the birth of Intuitionism. The second worry has to do with the continuum, the uncountable set of all real numbers. Uncountable, that means that there is no one-to-one correspondence between the real numbers in the continuum and the counting numbers, 0, 1, 2, 3. Okay, there are, in classical terms, more of them than there are counting numbers. Now, the continuum thus built is what I call brittle. It can be split at any point. For instance, you can take the set of all numbers, all real numbers less than 1/2, and all real numbers greater than or equal to 1/2. And the continuum is the union of those two sets. You split it very precisely and very cleanly at that point. Yet traditionally, historically, and many thinkers claim intuitively, that's not an accurate description of what a continuous manifold is, or what a continuum is. A continuum is something flowing, something viscous, is the term that I use, that cannot be split simply. And I've given you 3 quotes in the handout. I'll see one from the pre-Socratic philosopher Anaxagoras, who says the continuum can't be cut by an axe. And that's simply my way of putting it, is that if you try to cut it with an axe, like a viscous medium, something will stick to the axe and it will not be easily split. I've given you a quote from Kant, who uses the expression flowing, which actually stemmed from Aristotle and his successors, and a quotation from Brouwer himself in his dissertation in 1907, where he again says that a continuum is intuitively flowing. All right, and so the second problem with the classical continuum is that it's not flowing. It's not really that it's static, it's that it is splittable. Okay. And so these are the two motivations that lead to the birth of intuitionistic mathematics. Now, Bravo is not the first or the only, or the first person to worry about the problem of infinity. At the very beginnings of the set theoretic foundations, a mathematician called Leopold Kronecker objected severely to the introduction of infinite quantities into mathematics, and his solution was simply cut it all out. Okay, just forget it, do it. It's not mathematics, period. That was rather radical and didn't catch on. A second solution proposed in the early 20th century by a group of French speakers, including Lebesgue and Borel, thinkers that Brouwer calls proto-intuitionists, said, no, we've got to have infinite things in mathematics, but the only sorts of infinite sequences that we can continents that we can deal with mathematically are those that are given by algorithms, the sort of things that you can program a computer to produce. And the two examples of sequences that I gave you so far, the decimal expansion of 1/2 and the sequence 1/2, 1/2, 1/2. Those are certainly programmable. You can tell a computer how to generate the elements of those sequences. And so their suggestion was restrict the infinite part of mathematics to calculable. Brouwer gleefully and frequently pointed out that this is inadequate. I've given you a quote. Again, don't look for the quote, trust me, because otherwise we'll take longer than we should. I'll read the quotes that are really important. Where Brouwer simply points out something that we know, the set of all algorithms is countable. Algorithms are describable in language. The set of all linguistic expressions is countable. And if the continuum is made up of just of algorithmic reals, it's countable. The continuum should not be countable. Brouwer put it in terms of measure theory, the collection of algorithmic real numbers has measure 0, and that's not something that we want. A second solution was proposed by Hilbert. Yes, the great Hilbert. His view, and I've given you a quotation, is there ain't no infinity in the world. There is no infinite things in the world, and he actually, in a famous paper called On the Infinite, goes through the physics that was known at his time, arguing that no physical theory can provide us with grounds for saying that there are infinite objects, and there shouldn't be any in mathematics. Okay, so he's on the bandwagon of saying there shouldn't be these ungraspable infinite things in mathematics. But his solution was simply not to throw out the infinitary part of mathematics, but exile it. Put it in another region, which he called the ideal. It's not real. It's just thought entities that help us do our calculations of mathematics, but the real true mathematics is nothing but the natural numbers and arithmetic. And everything else, except finite arithmetic, goes into this netherworld of ideal entities. Right? Those are 2 ways, 3 actually, of dealing with the problem of infinity. None of these pre-intuitionist thinkers or non-intuitionist thinkers dealt explicitly with the problem of viscosity, of giving a continuum that has this intuitive property of flowing or stickiness. So Brouwer would have none of the Hilbertian relegation, none of the Hilbertian dismissal, and certainly on mathematical grounds, dismissed out of hand the proto-intuitionist algorithmic approach. For Brouwer, unlike Hilbert, the theory of real numbers, the theory of the continuum, the theory of functions, and everything built upon them, these are mathematics. This is what we're concerned with, and they are not some sort of ideal playthings that we can dismiss when we're talking real stuff. And so his task was to reinvent mathematics in a way that mathematical objects will be graspable, and that means that we build these objects out of our in a humanly graspable way, but a way that will preserve the uncountability of the continuum and its viscosity. And in particular, we view mathematical objects as things that grow over time. And we grasp them, I used to say we grasp them by the tail, but actually we grasp them by the head. We take what was given of them, and then we understand their principles of growth. And that's how we deal with mathematical knowledge. And there is nothing more. That's all, folks. There will be no more parts of mathematics that are in principle unreachable, in principle ungraspable. Okay, that's the credo. Right? That's the task that intuitionistic mathematics sets out to accomplish.
Yes. There are two words that I don't understand: humanly and in principle.
Okay.
So just take integers. There are unboundedly many of them. Take one that's way, way up there. There's a certain sense in which no human being, given the size of our cranium, can grasp, right, each individual one, right? I mean, we just can't. Our brains aren't big enough. Even if we could, you could. But then you might say, but in principle. But then, what's the principle of in principle if it's not human? I mean, what's human?
I'm going to say something to respond, but then I'm going to actually explicitly put some things in. Okay. I'll say something quickly to respond. Intuitionism includes a degree of idealization, just like many formal theories do. And what you are expressing is a view that is a view that has a name. It's called strict finiteness. Yep. And intuitionism, I'll simply say from the start, is not a form of strict finiteness. Okay. And so strict finitentism is a perfectly legitimate enterprise. It has its problems. There's a deep paradox in strict finitentism. But the paradox goes by different names. Famous one is Wang's paradox, but it's actually goes back before that. Intuitionism is not strict finitentism.
I have a very silly question. I didn't get Hilbert's view.
Hilbert's view.
I mean, I know probably it's not super important right now, but so I get what it means to say that there are no infinite things in physical reality, but then when he says that there are no infinity in proper mathematics, and it kind of distinguishes between ideal mathematics and real mathematics, I don't get the difference there. Like, I mean,
okay, the difference is actually very strictly drawn. Arithmetic is real mathematics. Finite arithmetic, adding and subtracting and multiplying. Okay. The generalization to recursive functions, Hilbert actually made a mistake, and he thought it was a generalization to primitive functions until that mistake was pointed out to him. That Hilbert's theory is a very well-developed theory, which is for me now just foil, and so I don't want to go too deeply into it. But the set of all real numbers is not a legitimate mathematical object. Okay, and as a consequence, we do set theory, we do build mathematics in the way that we intend. Okay, but we then make a separation between what he would call the ideal part and the contentful part, the part that is content or unhealthy, that is sometimes he calls intuitive, and only the intuitive part. This is an ontological position, not a mathematical position.
So basically, it's like Platon is with respect to, well, Platonist is he like Platonist with respect to arithmetics, and then it's like,
Yeah, well, he actually had a paper on that, but he was an empiricist. We'll put it that way, because he thinks that that natural numbers are a generalization of actual symbols written down. That's why he's called a formalist. Okay, but he's a sort of weak empiricist because he thinks of these things as types rather than tokens. But he would not answer to the focus because he thinks that they are firmly founded in actual observation. Okay, and this dispute was one of the important sociological events of the late around the 1920s and 1930s. The dispute between Hilbert and Brouwer led to many interesting. Hilbert fired Brouwer as the editor of Mathematische Annalen. Hilbert really, believed his view. His view also, we know now, was based on false. Fair enough?
Thank you. Yeah.
Good.
You have 25 minutes still, so we should.
All right. So basic objects. Intuitionism grows in time. Intuitionism assumes that its objects grow in time. Natural numbers, the simplest examples. I give you a quote where Brouwer says how they are generated over time. Each natural number is generated by an iterative but terminating process. That, for the moment, is not interesting to us. What's interesting to us are infinite sequences, which intuitionism calls infinitely proceeding sequence. An infinitely proceeding sequence, sigma, is given by a finite initial segment, what you can grasp, and a method for determining the future components. A method of generation has to be strong enough to yield a component of each stage. We have to be able to assert that for any n, there is an nth component. For any n, there is a q, such that q is the nth component. Real numbers are generated by infinitely proceeding sequences of rational numbers that can be shown to converge. And we say the two real numbers are equal when their sequences co-converge. But what kind of processes can we have to generate infinitely preceding sequences or real numbers in general? In particular, well, we got algorithms. Okay, an algorithm is clear. At each stage, there's only one possible choice for the component. Sequence alpha is given. Here's an example of an algorithm, the sequence that I gave you to start with. We know exactly how to get the nth component. And that we can call the real number 1/2. But there could be algorithms within algorithms. An example is the sequence that I'll call beta, which is given once again by an initial sequence, 0, 1/2, and the following rule. Rule goes like this. Calculate the decimal expansion pi, which we know we can do algorithmically. And as you're calculating it, at each stage of that calculation, determine the corresponding component of beta. Okay? And that corresponding component at the nth stage will be 1/2 minus 2 to the minus n plus 1. Okay? And so you're getting smaller and smaller components as you move along. Okay? And you keep doing this. We have an algorithm for pi, and now we have an algorithm for beta. If and when you get to a point where you have turned up 1 million consecutive sevens in the decimal expansion of pi. Okay, if you have turned up 1 million consecutive sevens in the decimal expansion of pi, which we haven't done yet, you stop at that point k, and you stay constant there. From that point on, the sequence is 1 minus 2 to the minus k plus 1, and it stays constant. Okay, and so this is a sequence, clearly converges, clearly gets closer and closer to 1/2 until and until it stops and stands still. It doesn't really stop, it just keeps giving the same thing. Okay, that's a perfectly legitimate sequence. Here's another kind of sequence. This is the kind that people like to glom onto. Sequences involving choice. Okay, the example is gamma, a sequence now called gamma. All right, the initial sequence is once again 0 and 1/2, and the principle is that at any point after that, you choose the rational number that either lies to the left of where you were, or stay where you are, or choose the rational number that lies to that lies 1/2 to the n plus 1 to the left, or stay where you are, or 1/2 to the n plus 1 to the right. And so after 1/2, you get you can either choose 1/4, stay at 1/2, or 3/4. If you've chosen 1/4, then you can either get 1/8, stay at 1/2, or 5/8. Stay at 1/4 or 5/8, and you keep going that way with no other principle of choice. Okay. Brouwer considers that a perfectly legitimate real number generator and a perfectly legitimate sequence. Don't get all excited about this notion of choice, because here I'm going to give you an example of a sequences that are not algorithmic, but nevertheless involve no choice. And these are sequences based on solving problems. They're called creating subject sequences, which get people all tingly, but it simply means that at pre-designated stages, ideal to the end of time, we check and see whether the mathematical community has solved a particular problem. The problem I like to use these days is Goldbach's conjecture. Not sure how many of you have heard of it. It says that every even number is the sum of 2 prime numbers. You may not believe that, but you can check it very, very far.
Greater than 2.
All right. Greater than 2. Greater than 0. All right. And unless you think one is a prime number and you can allow it to see.
One better not be prime.
But at any rate, this is a conjecture that has been interesting to mathematicians for years, and it has not yet been proven or refuted. And so what you do is you check at every set interval whether or not this proposition has been proven or refuted. If it has neither been proven or refuted, you give us an output 1/2, if this is the nth stage, plus -2 to the minus n. All right. And so you are, when n is even, you're going to be 1/2 plus something. When n is odd, you're going to be 1/2 minus something, but you're still getting closer and closer to 1/2. If and when the conjecture is resolved, you once again stand still, give the point at which the conjecture is resolved, and stay that way forever. So the elements of this real number generator, this sequence, oscillate, okay, on either side of 1/2, okay, so long as the conjecture remains undecided. As soon as or whenever and that conjecture is decided, it stays still. If the conjecture is decided at an odd stage, it stays still at less than 1/2. If it's decided at an even stage, it stays still at greater than 1/2. Okay. Notice, I pointed this out, that each one of the real numbers that I mentioned, alpha, the algorithmic beta algorithm within an algorithm, gamma, free choice, delta, creating subject, each one of them converges. Okay. They get closer and closer together. If they stand still, then they obviously converge, but if not, they get closer and closer. The components get closer and closer together. But we cannot say whether any of them co-converge. At this point, we have no idea whether any of them actually converge to the same thing. Okay, Brouwer showed how to deal with real numbers generated by these sorts of things. Any kind, algorithmic or what I call wiggly, how to calculate with them, how to form relations, to find functions among them. This is mathematics to the core. Real numbers, he says, now are graspable. They compose the continuum. There are functions from real numbers to real numbers. As in classical mathematics, there is idealization. Okay, we assume that the sequences will go on forever. We don't worry about whether we will run out of mathematicians to calculate or to work on solving problems. Okay, but unlike classical mathematics, we do not assume that all the components of a real number are given together. And that difference leads to deviations in classical mathematical counterparts. And here are some deviations. One has to do with logic. The law of excluded middle, for any proposition P, the sentence P or not P is a logical truth. And I bet most people here believe that. But intuitionistically, the real number gamma, that's the three choices, okay, it's a legitimate, graspable real number. We can calculate with it. We can say things about its relation to other real numbers. For instance, we can say that it's in the interval 0, 1, and if less than 0 or greater than 1, and it could achieve those. But we cannot say whether or not it's equal to a half. That is, we cannot assert either gamma equals alpha 1/2, or it is not the case that gamma equals alpha 1/2. The law of excluded middle does not hold. And in fact, with that, many other logical laws will fail. In particular, the law of double negation, from not P, we get P. I can show you later why. From this, I can show you why that law fails, which means you have to be very careful with indirect proofs. Okay, you can't simply prove something by contradiction, okay, because a contradiction will only get you not. All right, that's one deviation. Second deviation has to do with the continuum. Classically, as I pointed out to you, the continuum is splittable. For any real number R, we can split the continuum into a pair of distinct sets. The set of numbers less than R, the set of numbers greater than or equal to R. In particular, we could do it at 1/2. And there's a picture. Here, the continuum is split at 1/2. The blue side on the left, the red side on the right. Okay. Intuitionistically, we cannot split the continuum at 1/2 because we don't know where to put gamma. We can't determine which side gamma was, remember, is the free choice one. Delta, I'm sorry. Delta is the one that oscillates, right? And so we don't know whether delta is going to fall to the left or to the right. There's a reason that delta won't fall at 1/2, but I'll save that. And so we cannot split the continuum. There's going to be what I call viscosity. Try to cut it, and real numbers like delta will stick to the knife. All right. The third deviation has to do with functions. Classically, the simple step function, which is equal to 1 for all the numbers less than 1/2, equal to 2 for the numbers greater than or equal to 1/2, is totally defined. It's a total function, okay? For every real number, that real number has a value in this function, except intuitionistically, it is not a total function. We cannot calculate its value at beta. That was the one where you're waiting for to see whether there's a run of 1,000,000 sevens in the decimal expansion of pi, and you don't know whether beta is going to fall to the left of 1/2 or at 1/2. And so once again, you cannot define the function at beta. Okay, that function is not total classically, intuitionistically.
You cannot yet.
Wait. Okay.
How the idealizations are interacting with.
No. This is very much on the thing. Okay. Wait. All right. There can be no discontinuous total function. whenever there is a jump, we can always find a number like beta at which the function is not defined. Okay, this shows that the continuum is not countable, because if we were able to count the continuum, if we were able to set up a one-to-one function between the real numbers and the natural numbers, that function would be discontinuous. That function with that be discontinuous at every point. You know, I was mistaken yesterday. Okay. In fact, this doesn't mean that we can't calculate with numbers like beta and gamma and delta or define them. We can. We can calculate a continuous function like 1/2, you know, with those numbers, because these functions are calculated component. And as these components are generated, the components of the output will be generated. Continuous functions have that property. Okay. When discontinuous functions are functions that might depend on an infinite amount of input. We might have to wait till the end of time, and those functions, you know, therefore are not considered calculable. In fact, stronger theorem is that in intuitionism, every function on a closed interval is uniformly continuous, if you know about that. And I've mentioned that in the handout, but that's not something I'm going to go into. All right, that's it. That's the tour. All right, basic objects and 3 examples of deviation from classical mathematics. And so now comes the part where I'd like to set out the one set of philosophical assumptions, those concerning indeterminacy and those concerning time. We want to say that there is no indeterminacy in alpha, the algorithmic sequence, not even about its 1000th component, nor for that matter about the 64 trillionth digit in the decimal expansion of pi. We've calculated the 63 trillion at the moment. And we want to say that f, the function f, is not defined at beta. That was the one where you're looking for pi, 7s in pi, and that the continuum can't be split at gamma because there is it is indeterminate where these things sit on the line. But we can ask, if alpha's components already exist, what about betas and gammas? Okay, we need to give precision about the sources of indeterminacy and the faces of indeterminacy. All right, there's an epistemic face, knowledge. We don't know future values of alpha, of any of alpha. We'll take alpha out of it. Should be beta, gamma, delta. Okay, we have factually finite temporal grasp. We are temporally myopic. Okay. But there's also eternal indeterminacy. It is possible that we will go on forever calculating the decimal expansion of pi and never find that sought after terminal 7. Similarly, we may never find a non-Goldbach number, okay, though we don't manage to prove. Okay. Now, you may want to say, look, at the end of time, either we will found the counterexample to Goldbach's conjecture, or we will found the proof of Goldbach's conjecture, or since it's the end of time, we'll have seen that there is no counterexample. But the basic point of intuitionism is that we can't step out of our finite skins to look at things from the end of time. If we have to wait for an infinite time, we'll never get there. It's like we're in a car on a huge expanse. We can see where we've been and we can look forward to coming forks in the road, but we may even have a flow chart, but we can't step out into an infinite helicopter and survey the whole expanse, or an infinite time machine to transport us to the end of time. And with that epistemic indeterminacy, intuitionism puts on top of it a methodology, a discipline. Don't assert what you don't know, or at least what you can't know in a finite time. Don't assert the negation of what you can't or what you haven't disproved. Don't assert disjunctions without being able to assert a disjunct. Don't assert the existence of something without being able to construct it. That's why we can't say that alpha And we can't say that gamma is equal to alpha or gamma is not equal to alpha. To assert that right now, we would have to be looking from the infinite helicopter. And that's why we can't place gamma either to the right, this should be delta, either to the right or to the left of alpha, and why we can't calculate f of beta. Okay, but the restriction holds only for possibly eternal, not for temporary indeterminacy. Okay. We must be able to say that beta, the one that's looking at the decimal expansion of pi, has 64 trillionth component. Otherwise, we couldn't say that it was an infinite sequence. And we must say that delta, the one that's tracking the proofs of Goldbach's conjecture, has a 1000th component, even though we haven't looked at it that long. Otherwise, beta and gamma wouldn't be infinitely proceeding sequences. For this reason, we can now assert that 1000th component of delta is either to the left or to the right of 1/2, even though we don't know which. And so there is a distinction between epistemic myopia and methodological myopia. Methodologically, we are not myopic. Okay, we can't. And I'll come back to your specific example, but this is what I call the long view, and intuitionism takes it. There's a semantic phase. The truth value of the claim that gamma is greater than 1/2 may simply be indeterminate. Okay, and there's an ontological phase. We do not shun infinite objects. Alpha, beta, and gamma are infinite objects. Okay, but we deal with them in a finitary way. We calculate with them, we define real functions on them, those that can be calculated in a component by component manner. And we accept as total only functions whose outcome at each value is determined by a finite number of components. And that's actually why all functions are continuous. Objects in the world can be indeterminate in their properties. Objects need not be clearly distinguishable nor crisply decomposable. Those are properties of determinate objects. Gamma and 1/2 may be neither different nor identical. Okay, and the continuum is not crisply decomposable. As for the world, it may simply be indeterminate whether there is a non-Goldbach number. The world will be simply indeterminate. Okay, let me make 2 remarks. First, we track the local determinacy of our real numbers according to order relations. If we do that, the numbers like beta, gamma, and delta actually get increasingly determinate as they proceed. Right now, we can't determine whether or not delta, the Goldbach number, is less than 2 to the minus 50 or greater than it. But at the 50th stage, we can do that. Okay, but try as we might to define a real number, beta star or gamma star, where we know in advance that the relations of this number to 1/2 will remain eternally indeterminate, that we can't do. Okay, for if we know that the defining problem cannot be solved, we already know that the sequence will converge to 1/2. It would take an infinite helicopter to determine that the associated weight for an outcome will be in fact eternal. Okay, so the bottom line is that a sequence can grow forever. We may keep calculating and searching forever, but what we can know, and indeed what can be true, is only what we can learn in a finite time. When our finite grasp comes up against an infinite object, an infinite world, even if only potentially infinite, that's the source of indeterminacy in intuitionism. That 5 minutes? Great. Let me say something about time and then quickly say something about applications. Time for intuitionism is just the form of basic objects. And indeterminacy, since it rests on infinite weights, is intrinsically outbound. Okay, regarding the nature of time itself, well, time proceeds infinitely, but infinite sequences already give us that. And time is dynamic. I don't like to say a series. We can distinguish past, present, and future structure of an infinitely proceeding sequence. We have the fixed part, and we have the what we know currently about the rule, and we have the actual development. Time is indeterminate with respect to the future, not local indeterminacy. We say already that alpha and even beta and gamma have their nth components. Rather, it is a global indeterminacy. It may be indeterminate whether gamma ever settles down. And regarding the measuring of the extent of a moment, the creating subject sequences already show us that we can divide time into discrete stretches. In this sense, we can posit something like a Jamesian species present. But on the other hand, we can think of instants. An instant results from the natural infinite division of a stretch of time. This is an infinitely proceeding sequence. It could be expressed by beta or gamma or any similarly wiggly sequence. Time itself can be viewed as the sum of such instants, just like we view R. It is thus modeled by R, and it is itself viscous. Since we view time as dynamic, the appropriate metaphor is flowing. In giving this picture of time, Brouwer has actually achieved a historical breakthrough. Heretofore, the view that the continuum is unsplittable had gone hand in hand with the view that there are no instants, there are no points, and the quotations actually show you that. Intuitionism manages to have instants, to have points, but to maintain the flowing nature of time. Okay, that actually is my brief. I have 3 minutes. Okay, some speculations. This actually can sound very tame. It sounds wild, within mathematics, but it's all about mathematics. Okay, and the world here that's indeterminate, and the objects here that are indeterminate are mathematical objects. And in fact, that is the official view of intuitionism. Brouwer and Hiding, and now I'll quickly read you a quote from Brouwer, from the William Brouwer manuscript. The construction itself is an art, its application to the world, an evil parasite. Hiding. On the other hand, classical mathematics is simpler to apply, and any experimental result predicted by classical mathematics will also follow intuitionism. The official intuitionistic line is that applications are not our department. The fact is that Brouwer's remark was simply provocative. Hiding's was ingenuous, and I think it behooves us to, in fact, try seriously to think about what it would look like if we apply intuitionism to the world. And so we would say, we take the naive view that mathematics studies formal properties of empirical objects. Indeterminacy is such a property, okay? But maybe they're empirical objects. Maybe it's coin tosses that are giving us that indeterminacy. Maybe it's randomly generated numbers from Nicholas's random number generator. Okay, there are 2 ways in which one might see indeterminacy come into the physical world. One is it might simply be built in. There are simply indeterminate reality. It's indeterminate what the future is going to be, and it's indeterminate what it will ever become determinate. Indeterminacy is built in. Or classical matter, or one might say, wait, no, the reason that we want to consider indeterminacy is the intuitionistic reason. Classical mathematics pays too high a price for its determinacy. In fact, intuitionism has something to say to each of these views. Those who believe that there is a dice play in nature, keep in mind that this is only repeated temporary indeterminacy. Okay, if you use it to generate some measurable quantity, that quantity will encounter creeping determinacy, as I pointed out. Okay, and for the infinity data, we maintain the same discipline. That infinite helicopter may be lurking in some of the theorems that you use in order to do your mathematics. And in the handout, I've shown you a really basic theorem that fails because of an infinite helicopter, the mean value theorem. Okay. Finally, space and time. And they see that intuitionism is unsuited to study the spatial phenomena. And Brouwer himself said that intuitionism rejects Kant's view that space is an a priori form of intuition and accepts only his view that time is an a priori form of intuition. But this doesn't address the issue of spatial phenomena per se. Spatial indeterminacy, from our point of view now, is simply methodologically equivalent to a permanent temporal indeterminacy. Search if you can, you will not reach a determinate resolution to some question about space. And as for time, intuitionism idealizes the past. You have a fixed part of an infinitely proceeding sequence. And there's no upper limit to how much that could be. That is, time is a medium of research, but not as physical temporal phenomenon, the object of research. Okay. In reality, information is lost. And at an age where I use it more often than not. Memory, even collective memory, is bounded. In studying history, what I call, right, our tools are exactly the same. Temporary and permanent ignorance remain features of the reality, and there is an open past because there's an open future. The bottom line, if we want to apply intuitionism to physical thought, we have to think that the world and its objects are humanly, finitely graspable in this idealized way, and that there are no, in principle, unreachable truths. Thank you.
All right, so yeah, we're a bit over time, but since lunch is at 12:30, if you'll agree, we can continue for with 5 hours. Exactly. So we have, yeah. So please, Tim.
So there's a million things we could talk about. Let me just start with something very simple I didn't understand. On the methodological slide, you had one of the methodological things was don't assert a disjunction if you can't assert one of the disjuncts. Yeah.
Yes, but then I how do
I mean, this is associated with saying you reject the law of excluded middle.
yeah, that's why the law of excluded middle is rejected, but okay, but then I qualify it only for possibly a term. Okay, and so you can assert with respect to one of these big sequences that you don't know what the future is, but I can say right now that the one, say, the one having to do with the decimal expansion of pi, when we get to the 64 trillionth outcome, all right, either there will have been a final 7.5.
Right, I just don't understand that piece of math. So leave math aside.
Mhm.
Regular old coin, okay, dime, right? I hereby assert, and I think I'm correct to assert, it is lying either heads up or tails up.
Okay,
I cannot assert either one of those disjuncts, and now nobody in history ever will be able to rationally assert either of those
all
disjuncts.
right, so here's both of those points are actually addressed, so, right? The first one was temporary non-assertions. Let's assume that you're not going to erase it.
I don't know what if it was lying either heads or tails.
It was lying either heads or
Neither
tails.
anyone ever will.
Lying either heads or tails. In principle, there's a way of determining. You know, I could say, please lift your hand.
What's the principle? No, you can't. That's a counterfactual.
All right,
You're
I can
assuming
do-
truths of counterfactuals, but you're not.
certainly, I am assuming I am not Aristotelian. Okay, in a certain sense, I assume that, you know, well, I actually change it a little bit. I'll take the second one first. With respect to the past, with respect to now that we've erased the information, okay, then you have the situation of what I call the openness of the future. Creates the openness of the past. What was the case is no longer accessible. Okay, but there is, and therefore it is in fact indeterminate. Okay, what that was.
I just want to understand that.
That's-
If all you mean by that is we don't know and never
No,
will know.
is that-
If you mean there was no fact about
I
whether it
didn't
was
say-
high heads or tails, I don't
All
understand.
right, so that's actually, there's a famous, this is actually a question that Hillary Putnam addressed, very directly. Let me make a distinction. Everything I said here was using mathematical tools that we have. All right. When Hillary tried to apply this to the physical, he encountered exactly this example, and he changed it to use counterfactual in exactly that way. And that if in principle it would be possible to get that information, then I'm prepared to say that that information is determined.
And I'll just stop here.
Yeah, no, but that's a standard.
No, but Hillary does that. That's putting the cart before the horse. The reason I believe there's a fact about what I would have seen had I lifted my hand is because I think there's a fact about how it's lying, not the other way
I
around.
don't think there's anything in here that can.
You understand, Tim? So indeed, I also agree there is a fact here.
Yes.
So here there is, head or tail.
Yes.
Correct. But that doesn't mean that for this number, for instance, for gamma being larger or whatever.
No, but that's why I said
That's a different example.
the methodological thing was here, don't assert the disjunction if you can't assert it.
It doesn't mean that every disjunction, but not every disjunction.
That was still in mathematics. And secondly, if you don't have a method, it changes to don't assert a disjunction unless you have a method of being able to assert one of the disjuncts. Okay. And if, in principle, there's a method, even where counterfactual, that, that would still be. But these are part of the questions that Hillary and others dealt with when they tried to apply this, not the mathematics, but the logic to the physical world. I'm much more concerned here with applying the mathematics in the physical world. Okay, the logic, these are sort of well-hashed questions, and that one gives what answers one can, to those sorts of questions. Yes.
No, I can wait for the question, but I was wondering, can you, I see your point, but I wonder, can't you say that there's a difference between having a method at some point to determine and having a method at no point? Because it seems that in your example, at least before you shake your hand, there is at that point a method, right?
You think there's a method because you're making an assumption, which I think is correct, that the coin is lying one way or the other.
Actually,
Find out which it was by lifting your hand, which I didn't do. But then you can't.
There's the cart and the horse, actually.
Yeah, no.
That's the way that one in wearing that hat, the Putnam 1990s hat, says that you put the cart before the horse.
I'm sure.
And that's that saying that there's an actual fact of the matter is yes, I'm fine. Saying that there's an actual fact of the matter is saying that there is something that's assertive, rather than saying that there's a fact of the matter and we have to answer to it. And in fact, there's something. This is part two. There's earlier parts and later parts where I talk about how this affects the notion of reference. For instance, is this reference, right? And if I'm talking about one of these things, I've given what's called here a suitability to the meaning. Does that mean that I can't really refer to these things and that You know,
Right.
therefore there's nothing, and that's not the case. That's, you know, that's in fact not the case. The fact of the matter and what can be asserted go hand in hand. And, you know, trying to say that one is independent of the other is, you know, with that hat, it's a different color, people. With that hat, I would say that, you know, that's putting it right forward.
I mean, let me just say very quickly, let me give you a different example. This one I did because I can do it right here. I believe Socrates had a blood type,
Black one,
a blood type. He was
a blood
either
type, okay.
O, A, B, or AB. I don't know. Nobody knows. Nobody ever will know. And not in any realistic sense, is there a method or was there a method? Unless you say, oh, the method was if there had been,
This is the Putnam answer.
you know, blah, blah, blah. But then, and this is, yeah, he does the same thing by what did this dinosaur have a blue tongue? And he says, well, if there had been a human nearby, blah, blah, blah.
But
And you say,
without that,
you're going to accept truth values for these counterfactuals.
all right,
So the basis of truth values, it's the other way.
so take the empiricist other time. What cash value do I get out of the fact that Socrates had a blood type? All right, if it's something that is eternally lost. Okay, I don't know that it's eternally lost. I don't know, you know, that's one of the interesting things about, you know, indeterminacy. But we don't have examples, or I'm not going to give examples of problems that I know will be unsolvable. Maybe we can find pieces of his DNA. All right, maybe we can find traces that will give us enough information to know that sort of thing. We know that we now know that Beethoven's great-great-grandfather had an affair because we have pieces of his hair. And so, you know, the openness of the past, is subject to the same second level indeterminacy that I wanted to say the openness of the future is. Okay, if you know that it's indeterminate, you know, in these cases, you know, you already have a solution. Yes.
I want more to go to the open of the future because this seems to be less debatable. So a statement like it will rain in precisely 1 year time at Piccadilly Circus. Of course, we don't know, but this is not the interesting point. Is that, let's call this proposition P, is now P or not P necessarily true today? Because we just wait a year and in a finite time, we will know.
So here is where the work of what I call the different faces of indeterminacy come in. Okay. It is not assertable. Right now, it is not assertable. Okay. I leave the question of whether it's true, you know, there are some people who think that truth here has to be tensed. Right? I'm not claiming that truth has to be tensed. I'm saying that, you know, if it rains, you know, I hate future contingents in this case. You know, mathematics is happily free of that.
That's what you do with your delta of 1,000.
Right. But it's, you know, I say delta of 1,000, all right, because I have a method for already determining it. I would
So
say.
the delta, remind me, that's the one where you have
Delta
choices.
is the one you go by something.
Yeah.
Okay, and with respect to Piccadilly Circus, okay, if we take a certain amount of idealism, that the world isn't going to go away, that Piccadilly Circus isn't going to go away, that people, you know, that measurements, you know, can be made. If we take that, then I actually have no problem with asserting the excluded middle here, unlike Aristotle. Okay, but if the question is, Dummett's famous question, I take a blank field, you know, outside of London, you know, an empty field, and I say, a city someday will be built on this field. That I cannot say yes or no, because there I don't have any guarantee that I can determine that in a finite time. Okay, and so, you know, the difference between Piccadilly Circus, I won't assert yes or no, but I will assert, I won't assert yes, I won't assert no, but I am not myopic. I am prepared to say, yes, it will rain or it won't rain. Okay, that's different from Aristotle. But if I have something where I don't know that I can get an answer in a finite time, then that's the circumstance in which I will not assert the exclusion. Right, and so this is, less, in a certain sense, less radical, in a certain sense, more radical than things that people, want to talk about. Aristotle was, in a certain sense, stricter. Okay.
I would say if the world is really indeterministic, then this conjunction, raining or not raining, is
Right, that's
cannot be asserted.
that's, in fact, that's not a question into which I've gone. That's not something that I want. If the world is really indeterministic, I assumed that, the world was sufficiently deterministic so that this was like.
That would
so
be the
that
same
this was like,
your delta here with this goal.
so this was like,
To assume that the mathematicians will work in a predeterministic.
and that when we get to the end stage, they will either have solved it or not solved it. All right, if you want to build in determinism, then, then that's perfectly fine. But that's, that's a separate, separate consideration.
Another quick question, maybe we have time.
I had like, no, go on.
Follow up on this, but so but you don't allow that you might be mistaken about whether there won't be whether you are in a position, so whether you need a finite or no amount of time. So let's say that take the field outside London. Maybe you are mistaken because in 1 month they're gonna build a city there, and maybe there is already planned. Just you absolutely don't know about it. In this case,
Okay, there are two things. One is we make mistakes. All right, that's not built into any of this, but it can be. There's a simple way of modeling mistakes. Okay, that's, this is all assuming that we're mathematically, perfect in our calculations. If we're not, then there's certainly ways of modeling. The second thing is, a city will be built in the future, right? If in fact, using Nicholas's ideas, that's indeterminate, right? There's no plans, no, then I don't know whether I can determine that in a finite amount of time. Okay, and so then I would not use the excluded middle. If in fact there are plans that I'm unaware of, I made a mistake. That's,
so you think that you don't know about that.
and so that's, that's possible. It's not built into this machinery, but it can be built.
I'm pushing the same questions I asked from the beginning that they keep recurring. Even take this dumb example. It's the first time I've heard it. I guess, unless you mean by I, literally me, which is weirdly egocentric here. We know after a certain period of time, the sun is going to expand, it's going to engulf the earth. I'd say probably at that point, if no city had been built outside of London, it's game over, right? So again, if what's the restriction on this? And the other thing is, you did state up there an interesting claim, which is that time will go on forever. I don't know that.
Okay.
Right.
As
I mean,
said,
if you take GR seriously, there are models where it won't.
correct. This is simply, I'll answer the second question first, although the answers are similar. This is simply part of the idealization. All right, I think, we're doing idealized mathematics just as, no friction. If you want to build in those things, you have to see at which stage you're building it in. Are you building it in at the foundations of mathematics, or you're building it in at the, the point at which you're applying mathematics to, to physical or temporal reality. And you get very different responses in those two cases. In the first case, you idealize. In the second case, you don't, but then you may well have the open future because of indeterminacy. Now, as to, the question that mankind is going to end, there aren't going to be mathematicians. The universe, the earth is going to come to an end. Maybe we have, enough intelligence to keep it going a little bit longer. Or the solar system will implode, okay? Again, they're part of the idealization, and the dumbest example, plays into your point, because suppose we know that we may not know the precise number, but we know a large enough number such that by that time the Earth will have imploded. It simply then moves over into the area where we have a finite, we have finite bound of the information, and we treat it like information because of finite bound, and so therefore it's no longer unassertable that either by the end of the universe, once you put
I
it
still can't assert either of those. I can't assert either.
but again, we are, but that's back into the situation where we are not myopic.
Mhm.
That is, people mistake intuitionism to say you can never assert a squid middle if you don't have, the ability to assert one or the other of the disjuncts. That is not intuitionistic view. That's what I call a myopic view. And intuitionism does not go there. You can't go there if you believe that there are infinitely proceeding sequences. Okay. And so if you know that you can give a finite cap, right, but you're prepared to say that mankind will go on or do whatever idealizations, then you're fine.
Okay.
No, go.
Let's go for lunch. Thanks, Carl.